Hi everyone, welcome to class number 7. In this class, we are going to continue talking about pressure. Specifically, we are going to talk about some equations that allow us to calculate resultant force of hydrostatic pressure on different surfaces. It's going to be very exciting. I'll see you next slide. I'm going to start with a quick review of hydrostatic condition and hydrostatic equation that we discussed in previous session. The hydrostatic equation applies only if the fluid in your problem is in hydrostatic equilibrium. What is hydrostatic equilibrium? The definition for that would be if the acceleration of the fluid particle is 0 in the coordinate system that you selected, and also if the forces on the particle are only due to pressure and the weight of the particle, then the hydrostatic condition applies and you can use hydrostatic equation. All right, so I'm going to take a couple of seconds and write this definition under hydrostatic equilibrium for you. All right, so I have written the definition of hydrostatic equilibrium for you on this slide. Now I'm going to talk about more tangible sentences that describe this. So if a fluid is stationary, meaning that it's not moving, such as water in a lake or water in a tank or water behind a dam, right? Then hydrostatic equation will always apply without exception. Now, if a fluid is flowing, meaning that it's moving, for example, in a pipe system, right? The fluid is flowing, then hydrostatic equation will sometimes apply. Let me give you an example. Let's see that you have a circular pipe over here. To show that the pipe is circular, we usually use a notation like this. Like this, there we go. So, and the flow is in this direction. Hydrostatic equation, although we have the flow, although the water is moving horizontally, we can say that hydrostatic condition prevails in this vertical plane. Okay, so we can find out the pressure of the fluid over here and over here using the hydrostatic equation. All right, that was a short review to tell you when you can use hydrostatic equation. Now that you know about manometers and piezometers, I need to tell you that there is a downside to manometers and piezometers. What is the downside? So these devices are basically tubes, right? Glass tubes. So they can only measure pressures in a specific range, and that range is not that high. Because of that, there is another type of gauge called Bourdon gauge that you have probably seen around that can measure high pressure in different systems. In the video that you're going to watch right after I'm done talking in this slide, you're going to learn more about Bourdon gauges and how they work. They have a very interesting system of working actually. The topic that you are going to learn about today is very important when it comes to design of hydraulic structures such as tanks or dams. Have you ever noticed that there are different shapes of dams? Have you ever asked yourself why? Or have you ever noticed that the thickness of the dam at the bottom over here is higher or thicker than the thickness over here? And have you ever asked yourself why? Now you should have a good idea. You should, in your mind, think that this is due to pressure, right? Because as you go deeper, the pressure gets higher. But why different shapes? So the topic that you're going to learn today is going to be directly related to all of these questions. Before we move forward, I want you to watch this video after I'm done talking about this slide. It's a short video to get you introduced to some of these topics related to dams, and then we come back and move forward. Let's start with talking about uniform and hydrostatic pressure distribution. So I have my surface water over here, and then I have a panel inside that water. What's a panel? A panel or a plane surface is any surface that is flat or that can be idealized as if it were flat. For example, face of a dam is a panel. Now, if I ask you what is the pressure over here and what is the pressure over here, you are going to tell me that it's an easy question because the depth of point 1 is h1 and the depth of point 2 is h2. So we can use these two depths to find out the pressure using the hydrostatic pressure equation, h2, and then pressure at point 1 would be gamma h1. We all know that h2 is larger as h1. As a result of that, pressure at point 2 is larger than pressure at point 1. So, as an engineer, you should be able to sketch or draw pressure distributions. But there are a couple of rules that you need to keep in mind. First of all, pressure at every single point is represented by an arrow. Now, draw each arrow so that its length represents the magnitude of pressure. What do I mean by that? So pressure at point 2 is larger than point 1. So if this arrow represents pressure at point 2, then this arrow will represent pressure at point 1. And since pressure gets larger and larger as we go, as the depth increases, then this would be the pressure distribution. Now, it's another rule that you need to follow is that you need to draw each arrow so that the arrow is normal or perpendicular to the surface. Okay, that's very important. So the pressure is always perpendicular to the surface. Now, this pressure distribution that I drew over here, because it follows hydrostatic equation, it's called hydrostatic pressure distribution. When hydrostatic conditions prevail, any panel that is not horizontal is subjected to a hydrostatic pressure distribution. But you're going to ask a question, Professor, what if the panel is not, what if the panel is horizontal? And the answer to that would be, let's see what happens. So this is another scenario. We have water, and then we have a horizontal panel in the water. If I ask you what's the pressure over here and what's the pressure over here, you're going to say, well, the depth of both of these points is h. So the pressure for both of these points is going to be exactly the same thing. And if you draw the pressure distribution, it would be something like this, which in turn is going to be a uniform pressure distribution. Okay, is there any other condition that we can have uniform pressure distribution? The answer is yes. Let's say that we have our panel basically in a gas. In this case, I'm going to call like atmosphere. It could be any other type of gas too. So we have our panel, vertical panel, in a type of gas. In a gas, the pressure over here and over here are going to be exactly the same thing, and our pressure distribution is going to be uniform as well. So the point is, if you have a gas, your pressure distribution is going to be uniform. If you have a horizontal plane in the water, your pressure distribution is going to be uniform as well. For any other type, the pressure distribution is going to follow the hydrostatic pressure distribution. Now, this pressure distribution over a panel is going to generate a force, right? It's going to generate a force on the panel. What we are going to do in this class is going to find, first of all, the magnitude of that force, and then we are going to find the location of that force, the location that that force is exerted on the panel. The pressure force acts at a location called the center of pressure. So let me write it down actually. So it acts on a point like called center of pressure. It is usually actually symbolized by Cp, And the symbol for center of pressure is a circle with a plus inside. So if you have uniform distribution, center of pressure is going to be exactly, at the centroid of the geometric shape that you have, of the panel. And the centroid, or capital C, is symbolized using this symbol. It's a circle and then a plus, and then 2 of the quarters are basically like this. That's the symbol for centroid. What is a centroid for a geometric shape? So basically the centroid of an area can be thought of as the balance point of an area. So for uniform distribution, center of pressure is going to be exactly at the centroid. For hydrostatic pressure distribution, center of pressure and centroid are going to be different. And it does make sense, because if you take a look at this figure as example, which is in hydrostatic pressure, you'll see that the pressure is not uniform. Pressure in the bottom of the plate is higher than the top of the plate. So the center of pressure, or the place that the force is going to be exerted, is going to be different from the centroid of the shape. So to recap, we are going to, in this session, in these slides, we are going to find 2 things. First, we are going to find the magnitude of the resultant force due to the pressure distribution. We call it FR or FP. Also, we are going to find the location that this FR or FP is exerted. When designing gates, vessels, dams, or other bodies that are submerged in a liquid, it is important to be able to obtain the resultant force caused by the pressure loading of the liquid. And also, it is important to specify the location of this force on the body. In this slide, I'm going to talk about the magnitude of the force, and in next slide, I will talk about the location of the force. To generalize the development of the equation that I'm going to derive right now, I will consider a surface to be a flat plate of arbitrary shape that is submerged in the liquid. I have provided some photos for you in this slide. So the top photo is a 3D version, and the bottom photo is side view. Note that the origin of X and Y coordinate system is located at the surface of the liquid, so that the positive Y-axis extends downward along the plane of the plate. Now, before starting on the derivation of the formula, let's define some of the terms that we are going to use. First of all, Y. Y is the slant distance from the water surface to a spot on the plane. Next is angle theta. In your book, it's alpha, which is an angle between the water surface and the panel. Then dA is the differential area of a patch on the panel at position Y. You can see this is dA actually over here. This is the patch that I'm talking about, and over here as well. If I ask you what would be the depth of that patch, you would tell me that you have theta, you have Y, and you have H. So H, which is the depth, can be written as Y times sine of theta. So it would be Y times sine of theta. And if I ask you what's the pressure at that point, you would simply tell me that pressure would be equal to gamma times H. And I already know what H is, so it would be gamma Y sine of theta. Cool. So Now, the resultant force on the differential patch that I have can be written as dF equals pressure at that point times dA, which is the differential area of the patch. I already calculated the pressure at that point, so I'm going to replace it. Gamma y sine of theta times dA. Now, this is differential force only on top of that patch. However, over this panel, I can have many of these differential forces. So in order to calculate the resultant force, I need to simply integrate both sides of this equation over area of the panel. If you do that, this side of the equation, it would be F. I'm going to call it FR or FP. Your book calls it FP. I usually call it FR because it's a resultant force. And the other side of the equation would be, let me fix this first. The other side of the equation would be simply I can take out gamma and sine of theta. I can take those out of the integral, and it would be over A y dA. Now, this integral over here, only this part, this is called moment of area. Moment of area. And it can be approximated by y bar times A. Now, what is y bar? Y bar is simply the slant distance from the x-axis to the centroid of the panel. And the centroid is the geometric center of the area. So y is slant distance from x-axis to the centroid of the plate. So it would be, just to show you where it would be like a slant distance somewhere over here. We don't know exactly, would it be over here or here or here? That depends on the geometry of the shape, and because our shape is arbitrary, we don't know. We're just assuming it to derive the equation. So I'm going to remove it for now. Now, let's replace that to our equation. So our resultant force is equal to gamma sine of theta, and then instead of that integral, I'm going to put just y bar A. Now, so in this equation over here, I can calculate h bar, right? H bar would be equal to y bar times sine of theta. And then from this, if I solve it for y bar, it would be h bar divided by sine of theta. And what is h bar? H bar is simply the depth to the centroid of the submerged area. So I will actually define it later. Let's put it in this equation. So F R equals gamma sine of theta times, instead of y bar, I'm going to put h bar divided by sine of theta times area. Now, sine of theta cancels out with this, and my equation, final equation, is gamma h A and h bar. So Fr is the resultant force on the plate, gamma is the specific weight of the liquid, h bar is the depth to the centroid of the submerged area, so I'm going to define it here. This equation gives you the resulting force of a hydrostatic pressure over a randomly shaped plate or panel that you can use to find out the magnitude of force. And just to show you the location of h, or depth, so imagine if centroid is over here, then h bar will be something like this, h bar. In this slide, I told you about the Fr, or resultant force. In next slide, I'm going to show you where that resulting force is going to act. Now that we successfully derived an equation to calculate force due to the pressure distribution, or Fr, which can be calculated using this equation or this equation, and we know that this Fr, the resultant force, acts through the center of pressure. So we want to find the location of center of pressure. To do that, we need to write the equation for moment equilibrium, meaning that the torque due to the resultant force Fr must balance the torque due to each differential force dF, right? So actually, to write it down, I would write that the torque over x-axis for the resultant force should be balanced out with the torque, individual torques around x-axis for every differential force. So how do we calculate moment? So it is, you already know that moment is calculated by force times length to an axis, right? So we are calculating this over x-axis. So it would be Fr, which is our resultant force, times what is the length from Fr to our x-axis? That would be our Yp. That's the thing that we want to find, right? We want to find center of pressure, and Yp gives us the slant distance from x-axis to center of pressure. So I will write it over here. Would be Yp is equal to the integration over the entire area, and then we'll have dF, which is our differential force, times y. And y is the slant distance from x-axis to the patch that I showed you in previous slides. Remember that? All right. Now, I'm going to actually simplify this equation and move forward. I know that Fr can be replaced by gamma y bar sine of theta times area, and I know that dF I showed in previous slide that can be written by gamma y sine of theta, this time differential area, dA, right? So I have these two in mind, and I'm going to replace it to this star equation over here, and then it can be written as gamma y bar sine of theta times area times Yp is equal to integration over the area of the plane. But instead of dF, I'm going to replace it with gamma y sine of theta dA times y. Perfect. So a little bit of cleaning. I take gamma and sine of theta out of the integration, so it would be gamma sine of theta, and then integration over a, y to the power 2 dA. Perfect. Now I can cancel gamma and sine of theta out. There we go. And then rewrite the equation as Yp times y bar times a equals integration over a, y to the power 2 times dA. Now, this integration, y to the power 2 times dA, is very familiar, and it is called second moment of area. So I'm going to write the definition here. Second moment of area, or also it is called the area moment of inertia. Okay, now this integration usually is symbolized by I sub 0, and it can be defined as I bar plus y bar to the power 2 times area. So I'm going to replace the value of the integration with I sub 0. So it would be yp times y bar times a is equal to I bar, which is moment of inertia, plus y bar to the power 2 times a. Now, if you divide both sides of this equation by y bar times a, then as a result you would get yp equals y bar plus I bar divided by y bar times a. Okay, and this is the equation that we are looking for. We were looking for yp, right? And now we have an equation that gives us yp. Let me write down this equation over here a little bit bigger so we can discuss it. I'm going to write it with my red pen over here. So yp, which is this distance over here, is equal to y bar, which is the slant distance to centroid of the geometric shape, plus I bar, which is the moment of inertia, divided by y bar times area of the plane. All right. Now, you are going to ask me, Professor, now we have another problem, how to find I bar, and what is I bar? So I bar, as I said, is the moment of inertia, and is solely related to geometric shape that you're working with. So if you're working with a rectangle, if your plane is a rectangle, I bar has a specific value. If you're working with a triangle, I bar has a specific value. Okay, so I'm going to introduce you two tables that will give you the value of I bar. So based on the shape of the geometrical shape of your plane, you will refer to that table, you'll find the value of I bar, replace it in this equation, and find the value for yp. And yp is the slant distance to the center of pressure, what we were looking for. Now, there are a couple of notes that I want to mention. In your textbook, yp is represented by ycp, or the distance to center of pressure, cp, right? And in your book, Fr, or resultant force, is represented by Fp, force as a result of pressure. So if I use it interchangeably, I might use Ycp, Yp, or Fr, Fp to just make you familiar with different notations that we might use. The figure that you can see on your slide is basically figure A1 in the appendix of your textbook. Why is it important? Because it gives you the value for I bar for different geometrical shapes. Remember that I told you that I bar is solely related to geometrical shape of the gate or whatever you are working with. So for example, if you have a rectangular shape that you are working with, I bar can be calculated using this equation, in which B is the width and L and H is the length of the rectangular shape. Similarly, for other shapes, you can see the value of area and the value of I bar. In your book, it's I bar xx, meaning that it's moment of inertia over axis x, right? So I recommend, as you're working with different gates, you will see that usually rectangular gates, triangular gates, and circular gates are very important. So I recommend after a while having the equation for area and moment of inertia of these kind of gates in mind. It will help you when you are doing when you are solving a problem. It will be faster. In this example, we are going to determine the magnitude and location of the resultant force that the water pressure exerts on a circular plate. So this time we have a circular plate. This time I'm going to show the diagram and pressure distribution first. So this is the side view of that circular plate, and this is water. It's the surface of water that we have over here. Because hydrostatic pressure distribution is going to be there, I know that there's going to be some pressure over here, and the pressure at the bottom is going to be larger. This is hydrostatic pressure distribution. So I'm going to draw the hydrostatic distribution. Now, I know that because this is a circular plate, I know that the centroid of a circle is right at its center in the midpoint, right? So this distance over here is going to be h bar, which is 3 meters as given over here. And so yp is going to be lower, somewhere here, for example. That's going to be the location of the resultant force, which is yp. Now, I'm also going to find the resultant force itself, which is Fp or Fr. Now, to do that, the only thing that I need to do is to write the equation. My Fr, resultant force, is equal to gamma of water times h bar times area, which is equal to gamma of water is density, 1,000 kilograms per cubic meters times 9.81 gravity acceleration. The unit for that is meters squared seconds, times h bar is 3 meters, and then area is pi times radius to the power 2 times 1 to the power 2, and meters again, it would be, the final answer for my force would be 92.5 kilonewtons. And this is the final answer for force. Now, I have the force. The only thing that I need to find out is yp, the location of the force. And the location of the force, if I change the color of the pen, yp based on the formula is y bar plus ix bar, and remember ix bar should be for a circular plate here, divided by y bar times a. Now, ix bar, if you take a look at the figure A1 of your book or the slide that I presented, ix bar for a circular plate is equal to this, and this is radius to the power 2, to the power 4, sorry, to the power 4. Now, just plugging in the numbers, it would be 3 meters plus pi divided by 4, radius is 1 meters to the power 4, divided by 3 meter time pi, and then again 1 meter to the power, to the power 2. And based on that, your location of the resultant force would be 3.08 meters. And that's your final answer. Okay, so now I found yp to be 3.08 meters. Example number 2 is a very similar example to number 1, but this time our plate is triangular. Also, we have a tank that contains kerosene. Kerosene is a chemical that is used in many fields of engineering. So we want to find the force that kerosene exerts on this plate, this triangular plate, right? What I'm going to do, I'm going to call this point A and this point B, and I'm going to look at this system from side view. okay? And I'm going to draw this for you over here. So if this is my triangular plate, the side view of my triangular plate, this point is point A and this point is point B. I know that the height of this triangular plate is 4 feet given to us over here. 4 feet. Pressure at point A is 0 atmospheric pressure, and pressure at point B can be represented by this arrow. So we have a hydrostatic pressure like this. Now, what we are going to find is the magnitude of the force and also the location of center of pressure, or YP, which would be easy to find. Now, before doing that, we need to go to Appendix A of your textbook and find gamma, or specific weight for kerosene. So when you do that, you will find that specific weight for kerosene is equal to 50.88 pounds force divided by cubic feet. So this is something that we will find. Now, from the appendix part of your book, you will be able to find centroid and moment of inertia for a triangular plate. I'm going to write it over here for a triangle. H bar, which in this example equals to y bar. Why is that? Because theta is 0, right? We don't have a theta. Is equal to 1/3 of the height of the triangle. That's actually a good point to always remember. Whenever you have a triangle and you want to find the centroid of the triangle, have in mind that the centroid of a triangular gate is always 1/3 of its height from its base. So let me show it to you. The base of the triangle is over here, right? Over here. So if you want to find the centroid of the triangle, always measure from the base and go down 1/3 of its height. 1/3 of its height, which is 1.33. So this would be the centroid. The centroid of the triangle. Now, the other thing that you can find from the appendix of your book is I bar, or I bar x, or I bar xx. So if you take a look at the I bar for a triangle, it would be 1/36, and then you have BA to the power 3. What are B and A? So simply, B in this example would be 2, because that's the base of the triangle, so 2 feet. And then A in this example would be height of the triangle, which is 4 feet to the power 3. So I bar x, or I bar xx in this example is simply 3.556, and the units for that is feet to the power 4. Now that we have written all of these, we can simply calculate Fr, or the resultant force, to be gamma of kerosene H bar times A, and that would be 50.88 pounds force divided by cubic feet, times H bar is 1.33 feet, times area of triangle is simply half of 2 times 4. So Fr, if you put all the numbers together, would be 271 pounds force. That's Fr. Now we need to calculate Yp, or Ycp, which is the distance to center of pressure. If you do that, it would be Y bar plus I bar divided by Y bar times A. So y bar or h bar, they are equal right now. It would be 1.33 feet plus 3.556, 1.33 times area would be times 2 times 4, and if you calculate this, and the final answer would be 2 feet. In other words, again, as we expected, the center of pressure would be somewhere over here, and this would be center of pressure, and this is the resultant force. Notice that usually center of pressure is lower than centroid. Why is that? It's obvious. Take a look at the pressure distribution. Pressure distribution, the higher pressures are usually at the bottom of your tank or at the bottom of the dam that you are considering. That's why they built the dams thicker at the bottom, because they actually tolerate higher pressures there. Perfect. So this is simply how you calculate YP, or the location of center of pressure, and resultant force. All right, in this example, which is example 3.8 of your textbook, we have an elliptical gate that covers the end of a pipe with 4 meters in which is 4 meters in diameter. What's an elliptical pipe? So an elliptical gate basically looks like this, right? And the centroid of the elliptical shape is right in the middle of it. So if you go back to the appendix of your book, you will see that this would be A and this would be B, right in the middle of the elliptical shape. Okay, we're going to come back to it later. Basically, what we are going to find is the force F that is required to open the gate when water is 8 meters deep above the top of the pipe and the pipe is open to the atmosphere on the other side. We're going to neglect the weight of the gate as well. So I'm gonna basically strategize what I'm gonna do in this problem. So the first thing that I'm gonna do is to find FR, resultant force, right, as a result of the pressure distribution. Number two, I'm going to find the location of FR, or YP, right? And number three, I'm going to draw free body diagram because force F is involved. And then finally, I'm going to write the moment equilibrium about the hinge. Perfect. So in order to find FR, I need to find H bar. Okay, or depth to centroid of this elliptical shaped gate. So as I said, when you have an elliptical shape, you will go to the appendix figure A1 and you will find that the centroid of the elliptical shape is right in the middle of it. So in other words, it's right in the middle over here, right? Now, first of all, you need to find theta. Theta is this or this angle. So this is theta, right? So if I want to find the sine of theta, it would be 4 divided by 5, right? Perfect. Let's have this in mind. This is going to help us. So right now, I know that this distance that I'm going over by my purple pen is going to be 2.5 meters. However, that's the slant distance. What I care for is this depth. So that depth is going to be 2.5 times sine of theta, which is 4 divided by 5. So it is going to be 2 meters. Perfect. Now h bar is the distance from the surface of water all the way to the centroid. So this green distance over here would be 8 plus 2 equals 10 meters, which is my h bar, right? So h bar are calculated to be 10 meters. Now if I want the slant distance to the centroid, or y bar, that would be h bar divided by sine of theta, which would be 10 divided by 4 over 5. So it would be 12.5. Remember, y bar is the slant distance and h bar is depth. All right, so now I'm going to calculate FR, which is going to be gamma of water, h bar, and the area of the elliptical gate. So just to tell you, again, you go to figure A1 of your book and you will find out that the area of any elliptical shape would be pi A times B. What are A and B? This is B and this is A, right? So it would be equal to basically, I'm going to actually not write it here, I'm going to insert it into the equation. Gamma of water would be 98110 Newton divided by cubic meters times h bar we calculated to be 10 meters. And then finally, area would be pi times 2.5 times 2. And I'm going to write the answer in terms of millinewton to just avoid lots of decimal digits. It would be 1.54, and I'm going to write it in terms of million newtons. Okay, there we go. So that's our resultant force. Now, the last thing that we need to find, not the last thing, the next thing that we need to find is YP. And YP is equal to Y bar plus, in the denominator you have Y bar times A, and in the numerator you have I bar. So let me review. I bar for an elliptical shape would be simply pi A to the power 3B, and then you will have 4 in the denominator. Now I'm going to replace that into my equation. So YP would be equal to 12.5 meters plus, if you calculate that fraction, it would be equal to 0.125 meters, okay? And this would be 12.625 meters, and that's my YP, or the slant distance to center of pressure. All right, now I'm going to actually continue to next slide and show you how we can write the moment equilibrium about the hinge. I have summarized what we found in previous slide over here. So let's actually draw FR on this figure. So it would, FR would be acting somewhere over here, and that's our resultant force FR. And we know that YP is 12.65, meaning that the distance, if I change the color, the distance from here, the slant distance from here all the way to the surface of water to here, this distance is equal to 12.625 meters, right? All right, so what I'm going to do right now is to write down the moment equilibrium, meaning that summation of all the moments about the hinge is going to be 0, right? So we have only 2 forces acting over here. I am going to start with my FR. So it would be, let's say that this distance is equal to L. So I will have FR times L minus F, which is this force over here, times 5 meters, right? That's the length of the elliptical gate. Let me write this 5 a little bit better. 5 meters. This should be equal to 0. So FR times L is equal to 5F. And as a result of that, this force F is equal to FR L divided by 5. Now, how to find L? In order to find L, we need to find this distance, the slant distance over here, right? We have the depth, which is 8, so this is equal to basically h. If I want to find this distance, which would be y would be 8 divided by sine of theta, which is 8 divided by 4 divided by 5, which would be 10 meters. All right, so now L would be 12.625 minus 10 would be 2.625 meters. Now, going to insert all the numbers over here. FR is 1.54 times 10 to the power 6 Newton times 2.625 meters divided by 5. So if you calculate F and then convert it to kilonewtons, it would be F equals to 809 kilonewtons. Perfect. And this is how you incorporate all of your knowledge of physics to find out this force F. As students of fluid mechanics, you know things right now that normal people might not know, and you can apply your knowledge to real-life problems. For example, one of those problems could be flooded basement. Should you pump the water out immediately when your basement is flooded? The answer to that is no. But how can we use our knowledge of fluid mechanics to basically use that knowledge in this problem? First of all, let me tell you that this is the question of lots of people. And because of that, in 2004, the Federal Emergency Management Agency posted a bulletin telling people what to do when their basement is flooded. So the bulletin says that you should not pump the water out of your basement immediately. You should wait until the water outside of the basement is going down and the flood is done, and then pump it out. But let's see if we can find out why based on the fluid mechanics principles that we learned today. So I'm going to actually draw your basement, and obviously this is an exaggerated version of the basement, right? So in this basement, if it's been flooding, if it's been raining, the water level is over here and the basement is flooded as well. And I'm going to show the water level like this. Now, if I ask you to draw the hydrostatic pressure distribution, you would be like, okay, the hydrostatic pressure distribution would be something like this on the walls. And also there's going to be a uniform pressure distribution over here as well. So the walls and the floor of the basement is under pressure. Now, because there is water inside the basement as well, there's going to be a counterpart over here that cancels the force that is exerted to the wall of your basement. If you start to pump out this water, what will happen? Think about it. So if you pump out this water, there won't be any water over here. I'm just going to get rid of all these drawings. There won't be any water over here. So the resultant force, this resultant force, and this resultant force is going to exert a lot of pressure on the walls of your basement. So if these walls are not strong enough, they are going to simply collapse, right? That's why it's been recommended not to pump the water out of your basement and let the water level outside of the basement go down. Once the water level is down and down and down, then you can slowly pump out the water out of your basement. See, you can use all of these principles that you're learning in fluid mechanics and also in other courses as well to think about all simple daily problems that you experience every day. And that's the cool thing about fluid mechanics.